Hello and welcome to the 8th in a series of FTC webinars provided by Enable Training Consulting in conjunction with our colleagues at National Instruments. My name is Ben Zimmer from Enable Training Consulting, and as always I'm joined here by my colleague Greg Sullivan.
Hello.
And we're going to be presenting in this installment a series of advanced programming techniques to use with LabVIEW for the FTC competition. Let's begin with a quick review of what we did last week in the previous webinar. In webinar number 7, we investigated some more advanced programming techniques using a larger state machine. And in order to do that, we investigated the use of nested case structures. We talked about reusable code, and then we went ahead and solved a somewhat more complicated program than we had in the previous ones. Just a quick reminder, a nested case structure is when you use two or more case structures inside each other, and that allows you to create much more sophisticated logic scenarios and allows you to deal with multiple components and sensors. Reusable code is really beneficial and is an important piece of architecting your solution because it of course reduces the time it takes you to program, reduces the size of your program, and perhaps even more importantly makes it easier to debug your code. We talked about that as well. We see here this is the problem that we solved by implementing what we called a big state machine. It was a program that searched for an object and performed various different actions depending on whether a touch sensor or an ultrasonic sensor is pressed and also depending on the state. Rather than reviewing this long paragraph, let's review what a state diagram is. And we see that the state diagram we created was a much more compact way to look at that same problem definition. We see here that we transitioned from a start state into an idle state, and then when an ultrasonic detector detected an object, we started through this path through our states by having our motor start, move forward, move backwards, and ultimately stop if a touch sensor was pressed. Without going back into a lot of detail, because of course you can review that webinar online, the benefits of providing this kind of coding made it really simple to create the code and also to extend it as well. So in this webinar, as mentioned, we're going to talk about some advanced programming techniques. We're going to talk about reading from the NXT buttons. We're going to talk about Boolean flags. We're going to talk a little bit about using those NXT buttons to choose dynamic programs within our autonomous code. And within the concept of the teleop code, we're also going to talk about how to use Boolean flags and custom VIs or subroutines to perform slightly more sophisticated behavior and definitely custom behavior. So let's begin on the autonomous side. For this, the scenario is when we have multiple different strategies to implement in our autonomous code that may depend on perhaps the placement of the robot at the beginning of the game, it's really beneficial to be able to choose which autonomous strategy to run without having to have multiple autonomous codes sitting on the brick. And one of the ways to do that, as we'll see, is to use the buttons on the front of the NXT brick and the NXT display to ask and then answer questions so that the same autonomous code can run in different modes. So reading from the NXT buttons by using the read NXT buttons function allows us to read value from the left, right, and center buttons of the NXT. The end result of this function is to output a yes or no Boolean, which can be accessed right away, or we can store in a flag for later use, and we'll see that. Now, Boolean flags, as we've mentioned, are another slightly more advanced feature of NXT programming with LabVIEW that allow you to store data to be used later on. The basic idea is that they will store information such as Booleans, integers, or strings, and that by storing it in a particular location, they can be recalled later on. And the way we're going to implement this, as we'll see, is to store which button was pressed at the beginning of our autonomous mode to decide whether to turn right or left after an object has been detected and picked up. So we've talked about this idea of dynamic autonomous code that will allow your autonomous code to perform different actions based on an initial user input. We also talked about how the NXT front buttons are a great way to take this input in. So in this example, what we're going to do today is we're going to start with the familiar autonomous code that we talked about in one of the previous webinars. Essentially what that code does is it drives forward until it detects an object, picks up the object, and if the pickup was confirmed, it will turn and continue searching for an object to drop it. So we're going to take advantage of this code and just make some slight modifications to add to it this ability to run dynamically in either a right turn or a left turn configuration. We're going to do that by using the NXT button read and the Boolean flags. So this is a diagram kind of indicating the motivation as to why we might want to do this. Let's say in some generic FTC game scenario that we have an objective in the center of the field, and we're going to start either in position 1 or position 2. And placed in front of us will be an object. Well, if we want our autonomous code to go forward, deal with the object, and then turn and proceed to the objective, then clearly in scenario 1 we want to turn right before moving to the objective. In scenario 2 we want to turn left. But other than that, the code is exactly the same. So there's only a slight difference. And in this case, we can implement that really easily by just taking advantage of the read NXT buttons and the Boolean flag. So let's jump into LabVIEW and make those changes now. We'll begin by opening up our autonomous code. Let's take a quick look at it to remind ourselves how it behaved. We have the always present wait for enable, which is make sure that nothing happens within our autonomous code until the field control system software tells us that we're okay to go. We have then the key autonomous code inside a loop. We start off by resetting our servo positions, having a short delay, and then driving forward while checking the distance of and driving forward while checking the ultrasonic detector to determine a relative speed. When we have indeed detected that an object is there, we then perform some actions on the arm and gripper to lower the arm, open the gripper, close the gripper, and pick up the object, at the end of which we read the value from a touch sensor to verify that we have in fact grabbed an object. If we did get it, we present the success message on the screen, play a tone, and then move the object away. If the object has not been picked up by the touch sensor, then we present the failed message and then proceed accordingly. So what we're going to do now is make some pretty simple modifications to allow this code to behave dynamically. So let's go over here to the left-hand side. Remember that the decision we're going to make as to which right or left program to execute has to be before the field control system software tells us to go. So all of our modifications are actually going to be on the left-hand side of this wait for enable. So the first thing we're going to do is present the message onto the NXT screen. This makes sure that it's very easy for the team members to make the right decision, and they don't have to remember which button to press. The message is going to be presented. So we open the NXT I/O, choose one of the display control functions, and we are going to display text. We're going to start off with the string, so I'm going to create a constant on the string input saying turn left or, and move over a little bit. And this is going to be displayed in line 1, so I'm going to create a constant choosing line 1, and then use the control drag shortcut to make a copy of this to change the message for line 2 to be right. Then again, making good use of our NXT sequencing terminals, we've now presented our message. Compress things a little bit and make a little bit more room. So next we're going to place down the functions which will allow us to read our NXT buttons. So we're going to go to NXT I/O, complete, sensors, read NXT buttons. By placing this down and right-clicking to create a constant on the button selector, we can choose which button we want to read. So we're first going to read the left button. As always, use our NXT terminal to keep things sequenced up. And just to demonstrate, alternately, we can access the button read also from the sensor polymorphic function. By placing that down and choosing read NXT buttons, we can right-click, create a constant, and then choose the right button. It's the same function, just accessed from a different palette. Now what we want to do is we want to make sure that we don't just read the buttons at one instant, because it's just going to tell us at that moment whether the button has been pressed. What we really want to do is we want to wait until one of the buttons has been pressed. And so whenever we're waiting or we're checking something over and over again, that implies the need for a while loop. So let's place down from the NXT programming the while loop structure and wrap both of our button read functions in there. And really, we're going to leave the loop when either the left button or the right button has been pressed. So in order to implement that logic, we really need, from the NXT programming palette, Boolean subpalette, a function called OR. We take the output from each of the two functions and wire the result of that ORing to the loop condition terminal. That's going to make sure that this loop keeps running until one of them has been pressed. Taking our NXT terminal out, and what we're going to do is we're going to make a decision and we're going to store the result as to whether the right button has been pressed. So this right button is coming out of this Boolean wire, so we're going to take him to the edge of the terminal, and now we're going to store this in one of the Boolean flags. So the Boolean flags are available on NXT.io, complete, NXT flags. And here we choose whether we're going to set or get. In this case, because we're writing, we're going to do a set NXT flag function. Notice that it's got a polymorphic terminal selector, so we can choose the type of the flag. In this case, the default is what we want. We want to store a Boolean value, wire it up. We just have to be careful to make sure that we select the flag number. So we create a constant on top. And as long as we make sure that we're reading from the same flag number that we're writing to, that value is going to be available to us inside our loop. So we're okay to go here, but there's one cleanup task we're going to do, which is just to make sure that we clean and restore the NXT display. So again, by going NXT.io, display, and choosing from the polymorphic selector, restore display, wiring everything up, it's going to make sure that once we've made our autonomous selection, whether we're going to go left or right, that it cleans the NXT screen, and then we're ready to go for autonomous. So we're almost completely done here. We've made our selection. Now all we need to do is actually use this value somewhere. So let's go back inside our loop, inside our code, and really the behavior that we wanted to change was after an object has been found, whether we turn right or left before proceeding away. And that's this piece of code here. So what I'm going to do is I'm going to press the Control key and drag to make a little bit more space here. I'm going to read my NXT flag. So I've got a new function to put down. Again, from NXT.io, complete, NXT flags. Now we're going to get the flag, place it down, sequence it up using our NXT terminal wire. Just line everything up so it stays looking good. Choose which flag number we want to use. So I'm going to create a constant on the top, flag number 0, and use this value now to select what direction we're going to turn. So I'm going to create a case structure here, which will allow us to choose whether to turn right or left. Take our motor speed constants, put them inside the case structure, and just wire them through this way. And then take the value being read from the flag into the case selector. So if we're in the true case, we're going to turn in this direction. And if we're in the false case, we're going to go the opposite direction. So in my false case, I'm going to create constants for both of these. And instead of positive 50, negative 50 in order, we're going to just flip those values and do negative 50 and positive 50. And that's it. We've now implemented a dynamic autonomous code that starts off by presenting a prompt to the user, reads a button press, stores that value in a flag, and then inside our code uses that value to perform selective action depending on which button was pressed at the beginning. So let's transition now. I'm going to hand the microphone over to my colleague, and we're going to talk about some advanced teleop concepts.